Welcome to the deep dive. Today, we're looking at, well, a foundational piece of internet technology, but it's more than that. We're examining a real Jekyll and Hyde protocol. We are diving deep into HTTP2. It's the successor to the protocol that basically ran the web for, what, 2 decades?
Easily.
Yes.
Yeah, HTTP 1.1 was the workhorse for a very long time.
And when HTTP2 first rolled out, I mean, it was hailed as this performance savior, right? Designed specifically to crush latency, get rid of the overhead that just hobbled the internet under 1.1.
Absolutely. The promise was speed, a faster, much more efficient experience.
And, it delivered on that speed. It really did.
It did, for the most part.
But here's the twist. Here's the critical pivot for our discussion today. The complexity, the sheer technical engineering needed to get that efficiency. Well, it introduced entirely new and, frankly, deeply unsettling security risks.
Yeah, that's the Hyde side of the story.
We're looking at vulnerabilities that literally let attackers rewrite the record books for, well, internet devastation.
It's pretty staggering when you look at the numbers.
Our main subject today is the HTTP2 Rapid Reset DDoS technique, distributed denial of service. And the numbers, they're hard to wrap your head around. We saw huge platforms, Cloudflare, Google, weathering attacks that peaked over 398 million requests per second.
398 million RPS.
Yeah. And just for context, that single attack volume was like 3 times larger than any previous Layer 7 attack ever reported, ever.
And it's not just the volume, right? It's the efficiency of the attack itself that's really astonishing.
How so?
Well, you hear 398 million requests per second. You immediately picture this massive global botnet, millions of hacked computers.
So
right?
wait, you'd think so. A huge army.
But the reality, according to the security firms who dug into this, was that this record-breaking attack, this devastation, it was pulled off by what they called a modestly sized botnet.
Modestly sized. What does that even mean in this context?
Only about 20,000 compromised machines.
20,000 to generate nearly 400 million RPS. That ratio is wow.
That's the core of it. That ratio is why this deep dive is so crucial.
So that really frames the mission for us then. How does a botnet smaller than, I don't know, the population of a small city,
Right.
how does it generate a request volume that could, as one report put it, theoretically focus an entire web's worth of requests on a small number of targets?
It's a terrifying thought.
Because, I mean, the entire global web, all endpoints combined, usually sees somewhere between 1 and 3 billion total requests per second. This one attack was a significant chunk of that global total.
Exactly. So we need to peel back those layers. We need to really analyze how the performance features, the things designed for speed, were technically weaponized for this kind of scale.
We need to uncover the cost asymmetry, the subtle technical details behind that efficiency.
Precisely. And to do that, we really have to start with the problem HTTP2 was trying to solve in the first place. What was wrong with HTTP 1.1?
Okay, yeah. Let's unpack the web before HTTP2. It feels almost archaic thinking about it now. HTTP 1.1 sits way up at Layer 7, the application layer.
Built on top of TCP, IP, Ethernet, the usual stack.
Right, the foundational stuff. But by the 2010s, websites got so much richer, more complex, media heavy.
Yeah, JavaScript everywhere, huge images.
And the limitations of 1.1 became really, really painful.
The big one, the classic limitation, was head-of-line blocking. HOLB.
Ah, yes, HOLB.
If you picture a queue, right?
Yeah.
In HTTP 1.1, the network could only really process requests one after another serially within a single TCP connection.
And browsers limited those connections, didn't they? Like 6 per domain.
Exactly. Often 6 connections per host name. So if one request on one of those connections, say a big image file, took ages to download,
everything behind it on that same connection just stopped. Dead weight.
Like completely stalled. It was like waiting for one slow person at a turnstile, blocking everyone else behind them. It killed throughput, made pages feel incredibly slow.
And compounding that was just the nature of the protocol itself. It was all text, wasn't it? ASCII.
Pure text. Which sounds simple, but it meant tremendous overhead. Every single request carried these verbose, often redundant headers.
Things like user agent, accept encoding, cookies.
Over and over and over again, across maybe dozens of separate requests for a single page load. All that text flying back and forth on the wire.
That duplication, it must have been a massive waste of bandwidth, especially on slower connections.
Huge waste. Particularly bad on high latency mobile connections. You could have, say, 80% of the header info being identical across 50 requests for a page.
But no standard way to say ditto?
Nope. No standardized way to compress that or reference a redundancy efficiently.
So this inefficiency, this blocking, it basically forced developers into creating all these performance workarounds. I really remember the pain of dealing with these developer
Oh,
hacks.
yeah. They were really just signs that the protocol itself was broken for the modern web.
Mm.
Duct tape on a failing foundation.
What were some of the big ones? Concatenation.
Absolutely. Concatenation was huge, combining multiple CSS files or multiple JavaScript files into one giant file.
Just to cut down the number of HTTP requests.
Purely for that reason. Then you had image spriting. Remember that?
Ugh, yes. Bundling dozens of tiny navigation icons into one big image.
And then using CSS background positions, fiddly little pixel offsets, to show only the tiny bit you needed. Again, fewer requests.
It felt so fragile. And then there was domain sharding. That was the real act of desperation, wasn't it?
It really was. Because browsers limited you to, say, 6 concurrent TCP connections to mysite.com.
Developers would just invent new host names.
Right. They'd split content across static1.mysite.com, static2.mysite.com, images.mysite.com, just to trick the browser into opening maybe 12 or 18 or more connections in parallel.
Just to load those last few assets simultaneously, it really felt like you were fighting the protocol.
You absolutely were. And HTTP2 was specifically engineered to make all those hacks obsolete, to solve those fundamental flaws.
So what was the first big shift?
The first major technical change was ditching text for a binary framing layer.
Binary framing. Okay, sounds technical. Why is that better than text?
Instead of unstructured text lines, messages in H2 are formatted into defined binary packets. They're called frames. And every single frame gets assigned to a specific, unique stream identifier.
So it standardizes things.
Exactly. It standardizes the transmission. You use defined frames. You eliminate the ambiguity, the parsing errors that could happen with text. It makes processing much more efficient and less error-prone. Message boundaries are explicit. Easier for network gear, firewalls to inspect quickly.
Okay, that makes sense. But the real game changer, the feature everyone talks about, the one that tackled HLB head-on, was stream multiplexing, right?
Correct. Multiplexing is the absolute heart of H2.
So how does it work?
Instead of juggling those, say, 6 separate sequential TCP connections, HTTP2 establishes just one single persistent TCP connection at layer 4.
Just one.
Just one. And over that single connection, you can now interleave, or multiplex, many concurrent requests and their responses. Potentially thousands of logical streams flowing simultaneously.
How does the browser or server keep track?
Because every binary frame is tagged with its stream ID. So even if frames from different requests arrive out of order over that one TCP pipe, the client and server can reassemble the data for each stream correctly.
Wait a second. If you're sending thousands of requests over just one TCP connection, doesn't that just push the head-of-line blocking problem down a layer? From HTTP at layer 7 down to TCP at layer 4?
Ah, that is a brilliant question. And yes, that was a central architectural debate when H2 was being developed and adopted.
So if one TCP packet gets lost, doesn't it block all the streams using that connection until it's retransmitted?
You are exactly right. TCP itself is still serial. It's still ordered. So yes, a lost TCP packet can cause TCP-level HOLB, stalling all the multiplex streams riding on top of it temporarily.
So H2 didn't totally solve HOLB.
It didn't solve TCP HOLB, but by eliminating the application-level HOLB, the one request at a time per connection limit of H1.1, and by consolidating all the traffic onto one connection, H2 generally achieves much better overall flow control and congestion management than juggling 6 independent H1.1 connections ever could, especially when used efficiently.
Okay, that makes sense. Fewer connections to manage, less overhead, even with that underlying TCP risk. And speaking of overhead, what about those massive headers from the old days? H2 had something for that too, right? HPACK.
HTTP header compression, yes, absolutely crucial. It shrinks those huge repetitive header sizes dramatically.
How does it do that? Is it just like zip?
It's a bit more clever than just generic compression. It uses a couple of techniques. First, standard header fields get Huffman encoded, which gives some initial size reduction. But the real magic is that it maintains a shared compression context on both the client and the server.
A shared context, like a dictionary.
It's exactly like a dictionary, or maybe more like a highly efficient texting shorthand. It uses static tables for common headers and dynamic tables that track headers seen recently on that connection.
So instead of sending user agent Chrome blah, blah, blah every time.
Right. Instead of sending that long string over and over, the client or server might just send a tiny index number, maybe 1 or 2 bytes, that points to that exact string already stored in their shared dynamic table.
Wow. That must save a ton of data.
Potentially hundreds, even thousands of bytes per request. especially on a complex page load with many requests sharing similar headers. It dramatically cuts down the chattiness.
Okay, binary framing, multiplexing, HPACK hack. What else? Server push. Driven by the push promotes frame.
Server push, yeah. This was the protocol basically trying to formalize one of those developer hacks we talked about, inlining resources, but doing it in a smarter, standardized way.
How'd it work?
It allowed the server to proactively send resources, things CSS files, JavaScript fonts, that it logically predicted the client would need for the page, even before the client finished parsing the main HTML and explicitly asked for them.
So it cuts down on round trips. The browser doesn't have to wait, parse, then request.
Precisely. It minimizes that waterfall delay, the time spent waiting for the browser to discover dependencies and then go fetch them. It could make pages feel much faster.
Did the client have any control? What if it already had the file cached?
Good point. The client did retain control. It could refuse the push using a specific frame type, the RST stream frame, if it already had the resource cached or decided it didn't need it. That prevents wasted bandwidth.
RST stream. That sounds familiar. You mentioned that earlier.
Indeed, I did. That seemingly small, harmless RST frame designed for graceful cancellation. As we'll see very soon, that's the very mechanism that got weaponized.
Okay, so with all these innovations, binary, multiplexing, HPSAC, push H2 sounds like an absolute performance miracle on paper. A total home run.
It certainly looked that way.
But the reality, at least in the initial industry benchmarks and testing, it was a bit more nuanced, wasn't it? Some results were not as expected.
That definitely surprised a lot of people, yes. In some very specific raw throughput benchmarks, think simple, repeated API to API requests, small JSON payloads, low application complexity.
Like microservice communication.
Exactly. In those scenarios, some studies actually found that good old HTTP 1.1 was faster, sometimes nearly 3 times faster than H2.
Wait, how? Why would H2 be slower if it's meant to be more efficient? Where did the overhead come from?
The overhead largely came from the complexity tax of managing multiplexing itself. The server, and to some extent the client, has to do more work per connection in H2.
Like what?
Allocating and managing potentially thousands of logical streams, handling flow control for each, reassembling frames in the right order, maintaining those stateful HPACK decompression tables.
Ah, state management.
Right. In a simple scenario with only a few sequential requests, the setup and management cost of the H2 stream architecture, the internal locking needed to protect those shared data structures, could actually outweigh the benefits you got from compression and concurrency.
So raw throughput wasn't its strongest point in isolation.
Not always, no.
But the real value proposition of H2 wasn't simple API calls. It was loading complex, modern websites, right? Pages with tons of assets.
Correct. That's where it was designed to shine. When researchers tested it on, say, a typical real-world website, maybe a bootstrap template with 25 images, 6 JavaScript files, 7 CSS files.
A realistic load.
Exactly. In those tests, HTTP2 showed a clear and consistent advantage. It was faster, often shaving significant time off the total page load. One study mentioned cutting load time by half a second, which could push performance into that desirable sub-second range.
Especially with a CDN involved.
Definitely. The benefits were even more pronounced when combined with the content delivery network.
So this really highlights that the H2 advantages, like parallel loading over one connection, they really kick in when you actually have lots of parallel requests to make.
Precisely. It doesn't help much if you're just making 1 or 2 big sequential requests. The parallelism is key.
And that leads to another important point, doesn't it? Even with H2 being so good at conquering latency by reducing round trips, physics still matters.
Absolutely. Reducing the physical distance between the user and the server remains critical. CDNs are still a necessity, even with HTTP2, if you want to push performance to the absolute limit by minimizing that last mile latency.
So even H2 couldn't beat the speed of light. It needed CDNs for that physical proximity.
Right.
It's quite ironic then, isn't it, that the very features designed to conquer distance and latency through efficiency were the ones weaponized for massive destruction, creating a whole new layer of risk that proximity couldn't solve.
And that's the perfect transition point. We move from the promise, the efficiency dream of H2, to the catastrophic security risks that its complexity unleashed.
Right. The performance features, especially around stream management, became the weapon.
Exactly. They became the tools for these devastating attacks.
Okay, before we dive straight into rapid reset, maybe let's just quickly frame how DDoS attacks themselves have changed over time.
Good idea. We used to primarily worry about simple bandwidth floods, right? Layer 3, layer 4 attacks measured in gigabits per second, just overwhelming the network pipe with sheer volume,
Just clogging the pipes.
clogging the pipes. But the sophisticated threat now, for years really, has been the application layer attack, layer 7, measured not in bits, but in requests per second, RPS.
Why the shift to layer 7?
Because modern web applications aren't just static HTML files anymore. Every request can trigger significant server-side work, pulling data from databases, running complex authentication checks, executing business logic.
Each request costs the server CPU cycles, memory.
Exactly. So the attacker doesn't necessarily need to flood the network pipe anymore. They just need to send enough costly requests to exhaust the server's application resources, its CPU or memory. It's often much more efficient for the attacker.
And we were already seeing layer 7 attacks using HTTP2 even before Rapid Reset, weren't we? Leveraging its parallelism.
Yes, definitely. Since late 2021, security reports noted that a majority of the high-volume layer 7 attacks were already using H2's ability to send many requests in parallel over fewer connections. They were already high-rate attacks.
But Rapid Reset just took that to a whole different level, an entirely new category.
Completely. And the key to the Rapid Reset attack is the clever abuse of a perfectly legitimate fundamental protocol feature, that RSA stream frame we mentioned earlier.
The one clients use to cancel a download they don't need anymore.
Precisely. Clients are supposed to use it gracefully. Maybe you navigated away from a page, or the resource was already in your browser cache, so you send RSA stream to tell the server, never mind, stop sending that.
Okay, so how did the attackers abuse this?
They automated a blindingly fast, trivial pattern. They'd open a new request stream, they'd immediately, like microseconds later, send the RS stream frame to cancel it.
Okay.
And then they just repeat that. Request, cancel, request, cancel, request, cancel. Over and over again at immense scale. And crucially, they did this across multiple streams simultaneously on the same single TCP connection.
Request, cancel, flooding multiple streams on one connection. What does that achieve?
Oh, this is the genius or the malicious insight behind the attack.
Yeah.
It bypasses a key server defense mechanism.
Which is?
Most HTTP2 server implementations have a built-in limit on the number of concurrently open streams allowed per connection. It's often set to something reasonable, like 100 concurrent streams.
Right, to prevent one client from hogging all the server's resources by opening thousands of streams at once.
Exactly. It's a crucial resource exhaustion defense.
Ah.
But by sending the R stream immediately after the request headers.
Ah. The attacker cancels the stream before the server counts it towards that concurrency limit for too long?
Precisely. The server sees the stream open, starts processing maybe, but then immediately sees the R stream and marks the stream as closed or canceled. The stream state resets very quickly.
So the attacker effectively never hits the server's configured limit of, say, 100 active streams.
They never hit the concurrency ceiling because the streams are canceled almost instantly. This allows them to have an effectively indefinite number of requests in flight over that single connection.
Wow.
The only real limits become the client's ability to generate new stream IDs quickly enough and the raw network bandwidth available between the client and server.
And that's why just 20,000 bots could generate nearly 400 million requests per second. They weren't constrained by normal server limits.
They completely bypassed the intended stream concurrency controls by exploiting the stream lifecycle itself.
This brings us right to the idea of cost asymmetry, doesn't it? That's what makes DDoS attacks like this so effective.
Absolutely fundamental. The attacker, the client side, is doing almost nothing. They're sending tiny cancellation frames, literally just a few bytes for the RS2 stream frame. Their operational cost is near zero.
Almost free for them to send millions of these tiny resets.
Virtually free. But the server is forced to do a massive amount of disproportionately expensive work, even for requests that get canceled immediately.
Let's break that down. What work does the server have to do?
Okay, for every single stream initiated, even if it's canceled right away, the server generally has to, 1, allocate memory and internal data structures for that new stream. That costs resources.
Okay.
2, it has to parse the incoming request frames, especially the headers frame. And critically, it usually has to perform the complex, stateful HPACK header decompression. Remember how HPA uses those dynamic tables? That involves memory lookups and state management. It's not free.
So even if the request logic itself never runs, the setup is expensive.
The setup and the initial parsing are computationally intensive. The server might also need to do initial checks, like authentication or authorization lookups based on cookies in the headers, even before realizing the stream will be canceled.
So the cancellation arrives milliseconds later, but the server's already burned significant CPU cycles and allocated memory.
Precisely. And it gets even worse in common real-world setups, like when you have a CDN or a load balancer acting as a reverse proxy in front of the actual web servers.
How does that make it worse?
Because those front-end proxies are designed for speed. They might receive the request headers frame, perform the initial HPACK decompression, allocate their own stream tracking structures, and then immediately proxy the request onward to the back-end origin server.
Before the tiny RStream frame from the attacker has even arrived or been fully processed by the front-end proxy itself.
Exactly. The proxy fires off the request to the back-end almost instantly.
Which means the back-end server also starts allocating resources, parsing headers, doing HPACK decompression.
Right. It starts doing all that expensive work too, only for the front-end proxy to finally process the R stream a moment later and realize, oops, this request was canceled.
And then the proxy has to tell the backend to cancel too.
Yes. The proxy now has to generate another message, often forwarding the reset command to the backend server.
So you've multiplied the load. Both the front end and the back end did expensive work for nothing.
That's the amplification or multiplier effect.
Yeah.
The infrastructure isn't just doing expensive allocation and parsing once, it's doing it potentially multiple times, plus engaging in expensive inter-server communication, proxying the request, proxying the cancellation, all for a transaction that produced zero useful output.
Maximum pain for the server, minimum cost for the attacker. The perfect DDoS recipe.
Exactly. It achieves the core goal. Resource exhaustion, but with terrifying efficiency.
Now, when this attack first came to light, there was some debate, wasn't there, about whether to call it a vulnerability. Cloudflare initially labeled it a zero-day vulnerability.
Yes, and that term sparked some discussion. A zero-day usually implies a bug, a flaw in the code that needs a patch.
But others argued it wasn't really a bug.
Others, including some other infrastructure providers and researchers, argued it was more accurately described as an exploitable cost asymmetry, or perhaps an inherent protocol weakness, or an exploitable feature of H2 stream handling. They argued the implementations were often following the spec, but the spec itself allowed for this abusive behavior.
Does that distinction really matter, vulnerability versus asymmetry?
It matters hugely for how you think about defense. If it's just a bug, you patch the software, problem solved. But if it's an inherent asymmetry in the protocol design,
You can't just patch it away easily.
right, you might need more fundamental changes or rely on complex behavioral analysis and heuristics to detect the abuse pattern. It forces architects to potentially trade off some of that H2 efficiency for more resilience.
And the severity was undeniable, regardless of the label. Standard Layer 7 DDoS defenses, things like simple request rate limiting per IP address, they were basically useless here, weren't they?
Completely ineffective, because the attacker could generate millions of RPS from a single IP address over a single TCP connection without violating typical rate limits based on connection count or IP reputation.
Cloudflare even reported experiencing intermittent edge instability during the attacks. That sounds serious.
That's a very diplomatic way of saying parts of their massive global network were struggling to cope. It's a chilling admission of how close this attack vector came to causing systemic problems.
So what was the effective defense if rate limiting didn't work?
The consensus from the major platforms, like Google and Cloudflare, who weathered the worst of it, was that you needed to be immediate and decisive. The standard HTTP2 way of closing a connection is called the graceful go-away process.
Graceful go away. How does that work?
The server sends a go-away frame telling the client, stop sending new requests after stream ID X, but it allows any streams already in progress below that ID to finish normally. Then it waits a bit before finally closing the TCP connection. It's designed to be polite, to not break things unnecessarily.
But that politeness sounds like a liability against a malicious attacker doing rapid reset.
It was totally insufficient. That graceful period, the time between sending the go-away frame and actually tearing down the TCP connection, was still long enough for the attacker to fire off potentially tens of thousands more request cancel pairs.
They exploited the grace period itself.
They absolutely did. They exploited that latency gap. So the recommended mitigation, the effective defense, is much more aggressive.
What is it?
Upon detecting the rapid reset signature, which is basically an abnormally high rate of streams being opened and immediately canceled on a core stream, on a single connection, the server must react instantly. It should immediately send a go-away frame, maybe indicating no new streams are allowed at all, using a high last stream ID, and then immediately close the underlying TCP connection. No waiting, no grace period.
A scorched earth policy for that connection.
Exactly. If a client demonstrates that abusive pattern, you just cut them off completely right away. You can't afford to be polite.
And the industry response was quite coordinated, wasn't it? getting patches out?
Yes, that was a positive outcome. The big players who discovered and mitigated it alerted the key web server software vendors, Nginx, Apache HTTP Server, others, and worked with them to develop patches and implement these more aggressive connection closing strategies.
So the incident, while terrifying, actually forced an improvement in global DDoS resilience for H2.
In a way, yes. It turned into a catalyst for hardening server implementations against this specific type of protocol abuse. A very painful but necessary lesson.
Okay, so rapid reset weaponized stream efficiency and cancellation. But that wasn't the only dark side to H2's complexity, was it?
Not at all. That same complexity, especially around how messages are structured and interpreted, opened the door to other severe issues. This brings us to HTTP2 desync attacks, which is really a modern variant of classic request smuggling.
Request smuggling. That's a nasty one. It usually involves tricking a front-end proxy and a back-end server into disagreeing about where one request ends and the next one begins, right?
That's the core idea, yes. And the primary enabler for this in the HTTP2 world is a very common architectural pattern. HTTP2 downgrading.
Downgrading? You mean when the client talks H2, but the proxy talks H1.1 to the back end?
Precisely. It happens all the time. Your browser talks shiny, efficient H2 to the CDN or load balancer at the edge. But that edge server then translates or downgrades the request into the older text-based HTTP 1.1 format before sending it to the actual origin web server, which might only speak H1.1.
Why would that cause problems? Isn't it just a translation?
The flaw arises because H2 and H1.1 define message boundaries and interpret certain header semantics differently, especially when dealing with slightly unusual or malformed requests. If the front-end proxy doing the downgrade interprets the request one way,
But the back-end H1.1 server interprets the translated result differently.
they become desynchronized. The back-end might see the leftover part of the first request as the start of a completely new, unexpected second request.
And that second request could be malicious, injected by the attacker.
Exactly. The attacker crafts the initial H2 request in such a way that after the downgrade, part of it poisons the connection, allowing them to smuggle in a hidden request that gets processed potentially under another user's context or accesses resources it shouldn't.
How did H2's structure enable this ambiguity? Didn't binary framing make things clearer?
In some ways, yes, but H2 also introduced fundamental changes to the request structure itself.
Yeah.
It got rid of the classic HTTP 1.1 request line, GET index.html, HTTP 1.1.
Yeah. What replaced it?
It was replaced by mandatory pseudo-headers, special headers starting with a colon, like .method, .path, .scheme, and .authority.
So .method.get, .pathindex.html. That seems cleaner, actually. How did that enable smuggling?
Because they're just headers now, implementation inconsistencies crept in regarding how they were handled, especially during the downgrade to H1.1's single request line. For instance, the H2 standard, RFC 7540 initially, said you should only have one .path pseudo-header. Makes sense. But researchers found that some server implementations, maybe trying to be overly tolerant, would actually accept multiple .path headers in an H2 request.
Oh, so the front end might read the first .path?
And use that for its routing or logging.
Yeah.
But when it downgraded the request to H1.1, maybe it concatenated them, or maybe the backend server decided to only process the last path it saw in the translated headers.
Leading to total confusion about what resource was actually being requested.
Catastrophic confusion. Different parts of your infrastructure are processing different request targets based on the same initial request. That's a recipe for disaster, bypassing access controls, cache poisoning.
And we saw this lead to some really serious high-profile vulnerabilities, didn't we? Not just theoretical.
Oh, absolutely. Real-world impact. High-severity request smuggling flaws were found on major platforms, often resulting in cache poisoning, session hijacking, and credential theft.
Can you give us some examples?
Sure. There was a well-documented case involving Netflix. An attacker used a clever H2 desync vulnerability to essentially hijack how JavaScript files were being included.
What did that allow?
It allowed them to inject malicious JavaScript that executed in users' browsers, potentially stealing session cookies, passwords, even credit card details entered on the site.
Yeah.
It was recognized as critical, netting a $20,000 maximum bug bounty payout.
Wow, that's serious impact. What else?
There was another technique called request line injection. This one specifically exploited how some front-end proxies handle the downgrade of the .method pseudoheader.
The .method, like GET or post-T.
Right. The H2 spec is very strict. The .method value should be a single token, no spaces. But some front-end components, notably Apache's mod proxy in certain configurations, were found to be too tolerant. They would accept a dot method pseudoheader containing spaces.
Why would they allow spaces? That seems like an obvious violation.
It often comes down to historical reasons, maybe trying to be compatible with older, non-compliant clients, or just lax parsing during the complex downgrade process. When H2 features were bolted onto existing H1.1 proxies, sometimes the validation wasn't as strict as it should have been.
So what could an attacker do by injecting spaces into the dot method?
When the tolerant front end downgraded this request to HTTP 1.1, those spaces in the method essentially broke the structure of the resulting H1.1 request line. It allowed the attacker to inject trailing junk after the intended method and path.
Trailing junk. How does that help them?
That junk could be interpreted by the backend server in ways that bypassed security rules. For example, maybe a web application firewall, WAF, at the front end blocked requests to admin. But the attacker crafts a request like .method, getNoteAdmin HTTP 1.1.1, smuggled inside the original request via the .method space injection.
So the front end sees noteadmin and lets it through, but the back end gets confused by the junk and processes the hidden admin request.
Precisely. The injected junk desynchronizes the request parsing, allowing the attacker to bypass URL-based access controls or other filtering rules.
Nasty. Were there other major platforms affected by desync?
Yes. There were significant finds at Yahoo Verizon, where a desync flaw allowed attackers to leak sensitive OAuth authentication codes via the referer header by hijacking user sessions. That paid out a $7,000 bounty.
OAuth codes? That could let you impersonate users.
Definitely. And another one at Atlassian Jura, also exploiting desync, resulted in a $15,000 bounty. The core impact is usually the same. If an attacker can control how requests are interpreted across different systems in the chain, they can often hijack sessions, poison caches, bypass security controls, and steal data.
So beyond smuggling caused by downgrading, were there other implementation gaps or weaknesses found in H2 due to its complexity?
Yes, a few others are worth mentioning. One relates to flow control.
Flow control.
Yep.
That's to prevent overwhelming a slow receiver, right?
Exactly. H2 has mechanisms where the receiver can tell the sender, slow down, I need a break. Crucially, the standard, RFC 7540, specified that flow control limits should only apply to data frames the actual content being sent. Control frames like headers or settings or artstream should always get through regardless of flow control windows.
That makes sense. You need control messages to manage the flow itself.
Right, but implementation reviews found that some servers incorrectly applied flow control restrictions to non-data frames, like headers frames.
What happens then?
It could cause the connection to stall unexpectedly. If a client sent headers too quickly and the server mistakenly applied flow control to them, the client might get stuck waiting for a flow control window update that never comes for headers, potentially leading to deadlocks or denial of service. Misapplied flow control breaks the protocol's state machine.
Okay, what else? You mentioned priority earlier, that it didn't work out well.
Yes, the priority mechanism.
Right.
On paper, it sounded great. Streams could declare dependencies on other streams, like don't send image B until CSSA is done, and assign numerical weights from 1 to 256 to signal relative importance.
The goal being to optimize loading, load critical stuff first.
That was the goal. Optimize asset delivery, improve perceived performance. But in practice, it was widely considered a failure. It was incredibly complex to implement correctly and consistently. Server implementations varied wildly in how, or even if, they honored priorities. And it was also potentially abusable by malicious clients. They could try to manipulate priorities to starve critical server resources or cause denial of service.
So it was complex, inconsistent, and potentially dangerous.
Pretty much sums it up. Reflecting this reality, the updated HTTP2 specification, RFC 9013, formally deprecated the entire complex priority scheme from the original RFC 7540.
Wow, they just removed it.
They deprecated it, strongly recommending simpler approaches if prioritization is truly needed. It's a clear sign that the original mechanism's complexity just wasn't worth the trouble or the risk.
There's also a practical challenge for people trying to find these flaws, isn't there? The tooling complexity.
Oh, definitely. With HTTP 1.1, security researchers had it relatively easy. It was plain text. You could craft a malicious request using simple command line tools like netcat, or even just by typing into a telnet session.
Simple text manipulation.
Right. But HTTP2 is binary. And it's stateful. You can't just blast binary bytes at a server. You have to manage stream IDs correctly, format the frames precisely according to the spec, maintain the connection state, including those HPT dynamic tables.
So your basic command line tools are useless.
Completely useless for crafting the specific, often malformed or carefully sequenced requests needed for deep security testing, especially for things like desync attacks.
What do researchers use then?
They've had to develop highly specialized, sophisticated offensive toolkits specifically for H2 manipulation. This significantly raises the barrier to entry for security research and penetration testing compared to H1.1. Finding these subtle flaws requires much more effort and expertise.
And finally, given the chaos caused by things like desync, did the standards bodies try to tighten things up?
Yes, the newer RFC 9133, which obsoletes the original H2 spec, puts a much stronger emphasis on mandatory validation, specifically to combat request smuggling.
What kind of validation?
It explicitly states that implementations must strictly validate header field names and values before processing them, or, crucially, before forwarding them in a downgraded H1.1 request.
Specific rules?
Yes. Field names must not contain uppercase characters, H2 headers are lowercase, or invalid characters like colons, except for pseudo-headers, new lines, etc. Field values must be checked and potentially scrubbed of characters like null bytes, line feeds, or carriage returns, which are often used in smuggling attacks to trick parsers.
So basically, be strict. Don't tolerate weird input, especially if you're a proxy doing downgrading.
Exactly. If a front-end proxy fails to perform this strict validation before translating H2 to H1.1, it's essentially leaving the door wide open for desynchronization exploits. The message is clear. Robust validation is no longer optional. #tag_outro.
Okay, let's just take a step back and try to summarize the big picture here. What does all this mean for someone building web apps or just trying to understand how the modern internet works?
Well, I think the key takeaway is that HTTP2 really was a necessary evolution. It absolutely delivered on its core promise of better performance and efficiency.
Yeah, it killed off those awful developer hacks like spriting and concatenation.
Right. Features like multiplexing and HPT compression fundamentally changed how browsers load pages,
Right.
eliminating major bottlenecks from the H1.1 era. It objectively gave us a faster web experience in most real-world scenarios.
But it's a big but. That power, the very complexity needed to achieve that efficiency. It simultaneously created entirely new and very potent security attack surfaces.
That's the crux of it. We saw vulnerabilities emerge not just from simple coding errors, but from exploiting the intended features of the protocol itself.
Like abusing the RStream cancellation mechanism for massive cost asymmetry and rapid reset.
Or exploiting the ambiguities and stateful nature of the protocol, especially during common practices like H2 to H1.1 downgrading, which led to devastating request smuggling.
The central tension here seems undeniable, doesn't it? Complexity, especially when laser-focused on performance, often introduces fragility.
It really does. Any shortcut in implementation, any inconsistent interpretation of the standard between different components in the request chain, it can immediately become a critical, exploitable flaw.
And the consequences are severe. We're talking record-shattering DDoS attacks, serious request smuggling leading to credential theft and account takeovers.
It forces us to rethink defense. The defensive effort can't just be about filtering packets or blocking IPs anymore.
You have to understand the protocol itself. You need to know why that tiny RStream frame, when repeated millions of times, is so incredibly expensive for your servers.
Exactly. Defense have to move up the stack, understanding and controlling protocol-level features and behaviors, not just looking at network traffic volume.
So maybe here's a final provocative thought for you, the listener, to mull over.
Yeah.
The sheer scale of the rapid reset attack generated by that modest-sized botnet proved something profound. The barrier to entry for launching incredibly impactful application-layer DDoS attacks has dropped dramatically.
It doesn't take a nation-state anymore.
Right. So given this trend, and looking ahead at the increasing architectural shift towards even more complex, stateful protocols like HTTP2 becoming ubiquitous, and the emergence of HTTP3 running on the even more complex QUIC stack.
Which brings its own set of challenges.
Where should application architects and protocol designers draw the line? Is the relentless pursuit of raw performance and cutting-edge efficiency worth the inherent risk? Or should we start prioritizing simplicity, minimizing the attack surface, even if it means sacrificing some potential speed gains?
Knowing that complexity, almost inevitably it seems, introduces vulnerability.
It's a fundamental trade-off, isn't it? Efficiency versus security, complexity versus robustness. And it sits right at the foundation of how we build the internet going forward.